For almost 40 years, there's been this single material that seems to break the laws of physics. It conducts electricity perfectly, but in a way that should be, well, impossible. Today, we're finally cracking open the mystery of this impossible superconductor.
So think about this for a second. Imagine a perfect wire, one that could carry electricity and lose zero energy along the way. I mean, none at all. That's the whole dream of superconductivity, right? But what if you found a material that actually did this, but it did it in a way that just completely broke all the rules? Well, that is the puzzle at the heart of this explainer.
All right, let's do a quick refresher on what a superconductor actually is. In any normal wire, you've got electrons bumping into atoms, losing energy as heat. It's just friction, basically. But superconductors, they're totally different. Inside them, electrons just flow, zero resistance, which means absolutely no energy gets wasted. It's perfect efficiency. Now, here's the catch. For a long, long time, we only knew how to make this magic happen at just ridiculously cold temperatures. We're talking just a tiny fraction of a degree above absolute zero, the coldest anything can possibly be. And as you can imagine, that makes them a huge pain and super expensive to use in the real world. But then, back in the 80s, everything changed. Scientists stumbled upon this whole new class of materials that could superconduct at, well, comparatively warmer temperatures. I mean, still crazy cold by our standards, but for physics, it was a massive leap. And one of these materials in particular became the source of just endless fascination and, honestly, frustration. And that material is called YBCO. It stands for yttrium barium copper oxide. And for the better part of 4 decades, it has been one of the single biggest puzzles in all of material science. Let's just put this timeline into perspective for a minute. Superconductivity was first spotted way back in 1911. By 57, we had the Nobel Prize-winning BCS theory, which did a great job explaining how it works in those ultra-cold materials. It's all about how electrons pair up. But then, YBCO shows up in 1987, and it's superconducting at temperatures way too high for BCS theory to even apply. Our best explanation was suddenly useless. And so the mystery just sat there, unsolved, for decades. So you gotta ask, why was this so hard? I mean, we had the material right there in our hands. Why couldn't we just, look inside and see what the heck the electrons were doing? Based on everything we knew, we expected to see something pretty straightforward. Electrons pairing up, flowing nice and smoothly. But YBCO was just baffling. It worked at these high temperatures for no reason anyone could figure out, and its internal structure, the actual arrangement of its electrons, was a total black box. None of our best tools could get a clear look. The problem, it turns out, was YBCO itself. Its really complex atomic structure and the weird way its electrons behaved created this kind of natural camouflage. It's like trying to photograph a hummingbird's wings while it's flying. The very thing you want to study is what makes it impossible to get a sharp picture. So to solve this, scientists needed something totally new, not just a better microscope. They needed a whole new way of looking at the material, a way to basically hit pause on all that chaos and finally get a clear view. Okay, so their approach here was just brilliant. First, they had to grow this perfectly pure crystal of YBCO, no flaws. Then, and this is the really clever part, they blasted it with a super powerful magnetic field. What that does is it basically pins the electrons in place. It freezes them. And then, with everything locked down, they could finally use this brand new imaging technique to take the first real snapshot of what was going on inside. So for the first time in nearly 40 years, that quantum camouflage was just gone. Scientists were about to get their first real glimpse inside the impossible superconductor. And what they saw, it changed everything. It wasn't anything that anyone had predicted, and it finally gave them the answer they had been looking for all this time. I love this quote from the lead researcher. He said, "It was like switching on a light in a dark room. This wasn't just some small step forward. This was the big aha moment the whole field had been waiting on for almost half a century." So what was in that room once the lights came on? Well, it wasn't the smooth sea of electrons everyone thought they'd find. Nope. Instead, they saw electrons organized into these strange static stripes. Scientists have a name for this, a charge density wave. And here's the really wild part. This striped pattern, which you'd think would stop electricity from flowing, was somehow existing at the exact same time as perfect superconductivity.
The two things were tangled up together. So, what in the world is a charge density wave, or a CDW? The best way to think about it is like a recurring traffic jam on an electron highway. You get these static stripes where the electrons are all bunched up. That's the traffic jam. And then stripes where there are very few. It's an ordered, repeating pattern, but it's one that no one ever expected to find inside a perfect conductor. Okay, so we've solved a huge mystery. Awesome. But the really big question is, why does figuring out this one weird material matter so much? What does this actually unlock for us? It all comes back to this number 0, 0% energy loss. If we can get that to happen at room temperature, that's not just an improvement, that is a full-blown revolution.
And that right there is the holy grail. Now that we finally understand the bizarre physics behind YBCO, this weird dance between the electron stripes and the superconductivity, we basically have the instruction manual. We can start designing new materials from scratch, materials that are even better, that are more efficient, and that might, just might, work without needing any of that expensive cooling at all. And the applications, if we can pull that off, are just mind-boggling. I'm talking about a global power grid with zero waste. Think about maglev trains floating silently on powerful magnetic fields, or MRI machines that are way, way better than what we have now. Oh, and it would be a massive leap for building the powerful, stable quantum computers everyone's trying to make. This isn't just a science experiment, it's the key to a whole new era of technology. By cracking the YBCO code, we haven't just solved one mystery, we've invented a whole new way to look at the quantum world. And that leaves us with one last, really exciting question. Now that we finally have a flashlight that can see into these dark places, what other impossible materials are about to give up their secrets?